Magnetism basics. So if we think about magnets, right, think about maybe just a little bar magnet. It's got a north and a south. You might think about your refrigerator. Maybe you got a refrigerator at home, and it has a little door on it. It's got little magnets of different things stuck on there, right? So you have your little refrigerator magnets and so on. So what we'll look at here is how these magnets, how they work, right? What causes them to be magnetic? What causes the magnet to stick to the refrigerator door? Things of that nature. So we'll kind of look at this. And when we talk about magnetism, we look at the root cause of magnetism, again, just being a moving electric charge. So we could even look at something as simple as the balloon that we use in some of our electrostatic stuff. And you rub the balloon on some fabric, right? And we gave it some negative charge on there, right? And so that balloon then has negative charge, and it has an electric field, right, relative to that negative charge. And if we move that balloon, right, we take that balloon and kind of move it back and forth, move it around, you'll actually get a magnetic field, right, a magnetic field you'll be able to observe around that balloon. Now, obviously the balloon's not a very good magnet. We're not going to sit here and have to move this thing around so it'll stick to the refrigerator, because as soon as you stop moving it, it's not going to stick to the refrigerator anymore. So it's probably not really useful as a magnet in that sense. But the fact that it does this lets us see that, right, all we need is a moving electric charge, and we ought to be able to get this magnetism, this magnetic field effect to take place. And so we want to look at how that moving electric charge idea ends up as a bar magnet or a refrigerator magnet that sticks to the refrigerator, for example. So we'll start off small. We talked about an atom. We were talking about electrostatics. We talked about the nucleus in here in the center. All right, so we have the nucleus of the atom where the protons and the neutrons are. And then the electrons are out here, right, in the electron cloud. And so the electrons have some motion associated with them. There's motion in the fact they move around the nucleus, and there's some basic rotational behavior that they have. Typically that's been referred to as the spin of the electron. And this doesn't really mean in terms of the actual spinning itself, like it's like a basketball spinning around, anything like that, but that's the term that was used because it was thought it was similar to that idea. So that motion of the electrons then allows us then to look at the idea of some moving electric charge that eventually will give rise to our magnet over here. In most atoms, the motion and the spin and the behavior of the electrons all kind of balances out. So all the electrons, are moving around, but essentially their motion kind of cancels each other out. So we might have some motion we could represent by this vector. We have other motion we represent by that vector, and those just simply cancel each other out. That's typically what happens with most elements that we look at. The exceptions are iron. It's the main exception, the best substance that really gives us the magnetism. Cobalt and nickel. All of these have motions of electrons where they're not completely balanced out. So there's some electrons that are maybe moving in these directions if we're going to represent our motion this way. And so we've got 3, 4 total going this way and only 1 having motion that way. And so these cancel out, but we still have overall motion like this. And so that overall motion of the electrons then gives the idea of our magnetism. And so this atom of iron, right, if we take this as an atom of iron, we'll draw it with the dot here to be the atom, and we'll just draw an arrow through it right here, and that'll be our north, and that'll be our south. And so this is what's known as a magnetic dipole. Alright, so we have a magnetic dipole, and that is really the smallest magnet typically that you're going to have in nature, basically an atom of iron or cobalt or nickel. There's a few other elements that will have these magnetic properties that are naturally noticeable, but these are the main ones we'll look at. So we have our north and our south, and you always have a north and a south pole. Right? They're just opposite of each other in terms of their magnetism, kind of like positive and negative charges are opposite of each other in terms of their charge. And so our iron magnetic dipole here is our smallest magnet. Now, you may be familiar with the idea of the magnets. We looked at our bar magnets here. If I take a bar magnet here with a north and a south, and I bring another magnet nearby with a north and a south, you know that those two north poles there are going to repel each other. They'll push apart. If we had another magnet over here that was a north and a south, we know that the south and the north here would attract. Right? And we know that it wouldn't require any contact, so that lets us know then that there is a magnetic field that's associated with the magnetic poles on the magnets. And so on our diagram here for our magnetic dipole, we'll just draw some field lines here where it's a north and a south. Those would attract each other. So the field lines will actually kind of reach out around, right, from north to south. And we might have some more field lines, right, just going out around here, right? And so those are our field lines, and typically we'll draw the direction, the arrows, right, showing going out of the north and into the south. So very much like we did with electric charges, right, there's a particular direction associated with those field lines. So we have a magnetic field, right, magnetic field out around our dipole here. So let's kind of clear things up here. We have our dipole, right? We have a north and a south. Again, it's called a dipole because there are two poles, and there are always two magnetic poles. You're not going to have a north off somewhere by itself or a south off by itself. Right? Unlike positives and negatives, which you can have away from each other, your magnetic poles will always come in these pairs of north and south. So if we were to look at a bar magnet, again, so we have a magnet here, we have a south pole here and a north pole there. We know that that magnet has some magnetic field lines out around it, right? Magnetic field lines reaching out around the bar magnet itself. And so if we bring that near to a piece of iron, so we have another piece of iron here, right? It's not a magnet, right? Not a magnet, just a piece of iron or steel, right? So it could be like a paper clip or the surface of a refrigerator that the magnet might stick next to. It ends up sticking to the magnet. They end up attracting each other, right? They don't ever repel, they just attract each other. So what we want to look at is what's going on inside this piece of iron here that's not a magnet. And so the iron itself is made up of iron atoms, and each of those iron atoms essentially is a dipole. So we might be able to look at this section of the iron right in here, and maybe all of the little dipoles, all the atoms of iron in this area, are all lined up, right? And if so, we have all the dipoles aligned in here, then this section here is what's known as a magnetic domain. And so this area here is the next size magnet. So we have dipoles, that's your smallest magnet. If you get a bunch of dipoles all lined up in a region within this piece of iron, then that's known as a magnetic domain. And so you may have multiple areas in this piece of iron here where all these domains exist. And so I'm just drawing one arrow in each little domain, showing all the magnetic orientation or alignment of each of these dipoles in here. So this is not magnetic, and it's not magnetic as a whole because these domains are not lined up with each other. If we looked inside an actual magnet like this we have here, all of our domains in the magnet are all going to be lined up with each other, and their orientation determines where the north and the south pole, the end where all the north poles are pointing for the domains is the north, and where the tails of all the domains are is the south end here. And so this is magnetic because all these domains are lined up. This is not magnetic because they're not. But when this non-magnetic material then, this non-magnet in this case, when it's actually in the magnetic field, these magnetic field lines then cause the domains in our piece of iron, it will cause them to all line up with each other. And now this is a magnet. So now it is a magnet. Alright, it's just another bar magnet. Again, it has a south here and a north here. The south and the north attract each other. It basically duplicates itself in the other material. And so that's why they'll attract each other. So it temporarily makes this into a magnet. If we were to take the magnetic field away, then all these domains would end up coming back to their normal orientation, which is not lined up with each other. If you put a strong enough magnetic field on this piece of iron, you can get these domains to stick longer and stay in this particular orientation. But over time, they'll kind of gradually rotate back. Right? They'll kind of rotate around so that it's turned this way instead. And so that'll take place over time. Or if you just drop the magnet, it'll do that. If you heat it up, the same kind of thing will happen. Those domains will kind of go back to the unaligned. All right, so this over here is not a magnet, because the domains are not aligned with each other, and this now is a magnet because the domains are aligned with each other. This is basically how you magnetize things and how a magnet could be formed in the first place.